Networking, Part 3. In this nugget, we talk about networking. This is Part 3, where we'll talk about the various protocols and ports that are involved in networking for the A+ technician. This is going to involve several different protocols, such as NetBEUI, NetBIOS, but primarily it's TCP/IP and other protocols that take place over TCP/IP and which ports they need in order to operate. We'll also take a look at IP addressing. How come, what actually makes up an IP address? What is 192.168.1.5? What actually comprises that? It's actually all in binary. We'll see that shortly here. Also, we take a look at address classes, class A, B, and C, and some other things such as loopback addresses. We'll also look at TCP/IP configuration, just how to configure individual clients if you want to set up a static IP address. Otherwise, hopefully, you can depend upon DHCP for most of that. And we'll talk about DHCP here and how it can assign IP addresses to your clients automatically, as well as using DNS and what its job is and what would happen if DNS server were to go down. What a proxy server does, in addition to everything else, it also does something called network address translation. And then we look at automatic private IP addressing, which is somewhat related here to DHCP, because if the DHCP server is down, you might get a PIPA address. Alright, as we get started here talking about protocols, let's first of all identify what a protocol is. A protocol is just a set of rules that are determined to achieve a certain goal. It doesn't apply just to networking. It could apply to social situations. It could apply to a series of steps that are required to accomplish a work task. It could apply to a lot of different things. Of course, with networking, our set of rules will attempt to get us to make a connection and transmit data to a destination point. So that's what really a protocol is, and these are some of the common protocols that you'll see, and these are all listed with the A+ exam objectives. Now, in the past, and in the current objectives as well, NetBEUI and NetBIOS are very often listed closely together, which is a little bit deceiving because it almost makes them look as if they're the same thing, just two different names for the same thing. This is really not true at all. These are Microsoft protocols which are named similarly, but which are a little bit different actually. You see, NetBEUI is the NetBIOS extended user interface. So it involves NetBIOS, but it's not the same as NetBIOS. What's important to understand about NetBEUI is that it is a non-routable protocol. This means then that you can only use it in a single network. So therefore, it's ruled out for any kind of a larger corporate scale. This is something we used in early Windows operating systems, early Windows for work groups and so forth. You can't even really get NetBEUI anymore. You can download it and then install it on some current Windows operating systems. But out of the box, you can't even get NetBEUI by itself anymore. Some will also have it on a CD somewhere that you have to kind of dig around for it to find it on the operating system CD. But anyway, we generally try to avoid NetBEUI under almost any circumstance because since it's not routable, you also cannot use it on the internet. And everybody's got to have the internet these days. How do we ever live without it? So for that reason, again, NetBEUI is not a good solution. NetBIOS is a different item. NetBIOS can take place over TCP/IP. You can have TCP/IP as your main protocol that you use to communicate with and still be using NetBIOS. What it does is it provides three services to applications: name service, registration, and resolution. This relates to browse lists and things like this that we have in Windows networking, which allows you to double-click on Network Neighborhood and to be able to see other computers listed in Network Neighborhood. There's also session service, which is connection-oriented. This means an established connection will occur before transmission of data can take place. There's also datagram distribution, or also connectionless connections that are made. And this is something that has less significance, but just a couple of different ways of making a connection. Now, one thing to keep in mind here as well, and this is just the distinction I want to make clear about this. NetBEUI, okay, that was the first protocol we talked about, uses NetBIOS. Okay. However, NetBIOS does not depend upon NetBEUI. I can be using NetBIOS over TCP/IP, for example, and never have a concern for NetBEUI. All right. So just keep that kind of thing in mind, and you'll still have NetBIOS and Windows networks. Probably not see much of NetBEUI anymore. And then you'll also be working with TCP/IP. This, of course, is the main protocol we'll be working with these days because it's routable, it's what you use on the internet, and almost any major service with Microsoft is going to depend upon TCP/IP over the network. Well, when we take a look at TCP/IP, what is it? Well, it's an acronym standing for Transmission Control Protocol and then Internet Protocol. They're not completely the same thing, but we kind of think of them as a single unit. TCP is really just a connection-oriented protocol that has to have a connection to a destination or receive acknowledgments of data sent before it will continue to send more data. This contrasts with something else called UDP, which just kind of sends it out there and doesn't really have as much concern that the destination host receives it. And there's other checks and balances, included in the media access method, that will help to confirm that data actually is sent, but it's not built into the protocol with UDP, whereas TCP it is. Internet protocol is actually the IP address that you'll have. Okay, so that's how you're uniquely identified, or your computer is uniquely identified on the network. And then all the other protocols that we see down here that we'll be addressing occur over TCP IP. Oh, and I don't think I mentioned this, but this document's available for you up on nuggetlab.com. I was going to put all this on whiteboard, but gee, it's just, you can tell by looking, it was just way too much writing. So I didn't want to make you suffer through that much handwriting of mine. Now, the other protocols you might use would be SMTP and POP3, both related to email. The SMTP is the Simple Mail Transfer Protocol, and you use this to send email to one or more recipients. So, if you've set up Microsoft Outlook, for example, for an email account, then you probably have entered in somewhere in there an SMTP server. I think in my area for Cox Communications as our ISP, I think it's smtp.west.cox.net, something like that. So you just enter that sort of thing in, and then for the receiving of email, you'll enter in a POP3 address. This is just the third version, that's what the 3 is for, of the post office protocol. It simply downloads inbound email messages, normally on a scheduled basis if you're using, again, something like Outlook, every 15 minutes, every 5 minutes, whatever it is that you specify. There's also IMAP, which you don't really see a lot of that used quite yet, but it's kind of cool. What this is the Internet Message Access Protocol. You can use it to access email on a remote server, so you don't actually have to download it. But you can access it from your local client, across the internet, for example, and view it. And POP3, by contrast, actually downloads the email to your inbox. So it might be kind of useful for, storing your email somewhere else. Of course, if you're concerned about downloading email from your mail server and then later on having something catastrophic occur and you losing all your emails, if you choose not to delete the email when you download it from your server, that's an Outlook option, which is kind of beyond our scope, but at least it's available there. Then you can kind of keep a copy of your email up on your mail server. Now here I've just gone to the Add New Account dialog box for Outlook 2010 if I were to set my email up. It's going to be very similar across other versions of Outlook as well as many other email clients as well. You just have to fill in the blanks pretty much. But here I would identify my name. This is what will appear to people that receive my messages. This is the email address that people are going to reply to. And then here's my account type, POP3, or there's also IMAP, which you can see right here as well. I'm choosing a POP3, where I'll just enter in whatever the incoming mail server is. I just made up pop.nuggetlab.com, and likewise for outgoing, it's smtp.nuggetlab.com, but you'll have to check with your ISP to identify what your actual server should be. Could also be an IP address, but normally we don't need to do that anymore because these should be resolvable on the internet without requiring an IP address. Then there's the logon information here, just whatever credentials your ISP has given you as well, and a password. That's pretty much it. At this point, using Outlook, I would normally test the account settings, but since this is all totally bogus, I know it's not going to go anywhere. But that's generally the idea of how you would set up your email using POP3 and SMTP settings. Other settings that we would have here, of course, would be HTML. This is just not really a protocol so much as it is a language, okay? So it probably doesn't really even belong on this page, but as long as I'm on the H's, I thought I'd throw it in there. This is web page code that defines how the web page appears in the browser. So it identifies what color of the font you're going to use, what size of the font there's going to be, where a picture is going to appear, where a button's going to be that you can click on, and the like. HTTP is the protocol that we use to access this HTML content. So Hypertext Transfer Protocol is what that stands for, and you need to know that you'll use port 80. I have another document available for you as well that will identify the various ports that you may need to know about. Also, there's HTTPS. What this is, it's going to be Hypertext Transport Protocol. It's secure in that the HTTPS here actually stands for SSL, but it also means that it's secure. And it's going to combine HTTP and SSL to get us a secure connection. Do need to know that it'll use port 443. If you access a website that's maybe your bank's website or a credit card or some other financial institution. When you're logging into any kind of a account, normally it's going to start with this HTTPS for you. And then SSL is the secure part of HTTPS. This is going to use something called the Secure Sockets Layer. This will use certificates to provide encryption as well as server authentication. That way we can be sure that we really are connecting to the bank that we think we're connecting to. For example, if the banking website is www.bank.com, then it should have a certificate that matches that, and that would be part of the server authentication. Sometimes organizations will change the name of their web server so it doesn't exactly match their certificate anymore. So for example, it might be www.one.bank.com or something like that. Well, now the name has changed, and so sometimes you'll get a little message to that effect. And if you're confident that it really is the appropriate location, you can go ahead and click past the message and go on to the page. Let me go ahead and show you here what I mean. Now then, here by way of example, notice that I've gone to beta.cbtnuggets.com. That's because our current website is undergoing a revision change, a design change, and at this time, our certificates are not going to match the normal cbtnuggets.com website. As a result, if I go over here and try to do something like sign in, it's going to see an issue with my certificates. Now, sometimes it may show you this page right here, depending on which browser you're using. There's also with Google Chrome, it looks similar, but just a little bit different. So this is basically telling me that there is a problem with it because it does not match up. The certificate name does not match up with the actual page it was trying to go to. So if I'm confident that this is the right location, I could just click continue to this website, and I will go ahead and do so now. And then at that point, I can also look at more information about this certificate error that we see. And then I'll go ahead and click Certificate Error and View Certificates, and you can see here that it was trying to go to secure.cbtnuggets.com. In reality, somewhere in the new web design, maybe it was beta.secure.cbtnuggets.com or something like that, but I don't really know what it was, but it didn't match up anymore, so that's why we got the certificate problem that we saw here in the interface just a moment ago. Now, we talked about Telnet in a previous nugget where we just used it as an example of how to remotely connect to a server or some other desktop client. And you can just from a command line then pretty much run that remote computer the same as if you were seated locally at that machine. Any command you type in from that command line, a Telnet command line, will actually be performed on that remote destination. And the difference is really pretty much transparent for the most part. Then we also have the ability to use FTP. This is File Transfer Protocol. Still a pretty good way to transfer files. We've done this in the past quite a lot from a command line. Then it's gotten a little bit easier because you can now click on a link in a web page and it'll download it using FTP very often to your computer. But it just kind of helps to conceal the fact that you have to use FTP there. Here's just some examples of this. If I just do a FTP and then a space, that tells it I'm going to use an FTP prompt, a space to ftp.accusource.net, which is one of my domains, and press enter, then you can see here that I'm going to have to enter in some credentials, and it's asking for a user here, and then it would ask for a password. I'm just pressing enter here and closing out right now. But that's one way I would be able to connect. The other way I might be able to connect would be if I had a client like what I'm using here, and this is FileZilla, which is what I prefer. And so if I again wanted to FTP to it, in this case it uses FTP ES or FTP over explicit TLS SSL, so it's an encrypted connection, which is actually pretty good because in the past FTP logins took place in plain text, and anybody that was sniffing packets on the wire would be able to pick up those passwords with very little effort of any kind. So then you would enter in your credentials, and then you'd be able to make the connection, again, using something like a client like we see here. And then although you saw me enter in ftp.accusource.net, just note that with FTP as well as things like Telnet and many other ways of connecting to remote clients, you don't have to enter in the name of the computer. If you know its IP address, that also is an acceptable way to do so. The advantage of using the name instead of IP address, first of all, is that it's simply easier to remember a name than an IP address. Secondly, using DNS servers, if the IP address of the server changes, then you're just kind of left with having to learn the new IP address for making your FTP connection. But if you use DNS, then the IP address changes in DNS, and all you have to remember is the same name that you've already been using. So that's just a little advantage of using the names as opposed to IP addresses here, especially for things such as FTP. And then don't forget the ports are 20 and 21, and you may need to make exceptions for that in your firewall. And then I talked to you about some ports that you would need to know about as well. I've also got a document here called Common Protocols and Ports. For HTTP, I think you probably already know, just use port 80 for general web browsing. HTTPS uses 443. Both of these can be changed if the webmaster so decides that they want to do so, but then you would have to know what port to type in the actual URL. It would be just, www.accusource.net : and then 457 or whatever port number you wanted to change that to. And then for FTP, we have 20 and 21 need to be open. And by the way, one reason why I need to know which port numbers these protocols use is because if you have to administer a firewall, you may need to open up certain ports. For example, maybe behind my firewall, we have an FTP server that we want to allow our customers to download files of. Maybe it's files of our product brochures or something like this. Well, if that's the case, then we want to open up the ports necessary to allow them to access FTP. And 20 and 21 manage the control and data streams for FTP. And then Post Office Protocol, if we want our clients to be able to connect into our server, for example, we might need to open up port 110 here to allow people to receive email. SMTP uses 25, Telnet uses 23, SNMP, this is not to be confused with SMTP because they sound and look a lot alike. This is different though. This is simple network monitoring protocol, and this is useful because in a lot of organizations there may be a software piece that will be able to scan and accept traps from all of the clients and servers on the network. And these traps would then have status information, such as whether or not they are having some kind of a problem, or there's a hardware failure, or just about any other kind of thing. There's a great deal of variety and flexibility in what you can monitor with SNMP. So you can monitor just about every aspect of a computer. There's also IMAP, which we talked about earlier as well, and that needs TCP port 43. By the way, some things need TCP and UDP ports, and you can see that those are listed here as well. Now, at various times, you've heard me reference IP addresses, and we've even seen several IP addresses throughout this series. What I want to tell you in this section is what those IP address numbers mean. Now, in order to properly configure a computer with an IP address, you have to understand a number like this one. Right there. I'd be looking at that and say, James, that doesn't mean a whole awful lot to me, so thank you very little. Well, actually, this is an IP address. It's just that this is how your computer sees it. Now, if you want to make it a little bit easier, you can break that up into 8 octets, because you see what this is? It's 32-bit positions. Okay? With IP addressing in version 4, you have 32-bit positions. If you want to break that up into 4 octets, then you can break it up like this. So there's 4 bits, or rather 8 bits there. Here's 8 bits here, separated by periods. Here's 8 bits here, and here's 8 bits here. Makes it a little bit easier for humans to read, although by looking at this, many of us still will not know what in the world the IP address is that we're trying to get to. You know what that number is? Us humans would read that out loud as 192.168.1.227. That's kind of hard to decipher from just looking at that, though, isn't it? The reason why it's a little bit challenging right now is because we don't yet understand, or we haven't yet reached, what each one of these bit positions mean. First thing to understand is that in binary, a 0 does not mean a 0, and a 1 does not mean a 1. We're not talking about literal numbers here. All the zeros and the ones mean are whether or not we count that bit position. So in this case, the far right bit position in this octet right here, we would count that one. These remaining 7 bit positions in this octet, we would not count. So let's go ahead and take a look at how we would add up our numbers here for IP addressing. So let's go ahead and decipher all of these octets. I'm just going to actually go to this one right now, this third one, to make it easy. Notice that in our IP address, the third octet in normal numbers, so to speak, is a 1. Okay, that's what we see right there. In binary, in that octet, it's also 1. Now, it's not because we have this 1 right here, because remember, a 1 does not mean a 1 in binary. It just means that something's turned on. Each one of these 8-bit positions corresponds to this number line that we see down here. So since we see the first bit position is turned on there, we know that if we correspond that to this number line, that must mean that's the number 1. Since all the rest of these are off, then none of the rest of these numbers count. So the only number that counts is the 1. All right? So that's how you work with this. And that's how you're able to convert from binary numbering like this into decimal numbers like this down here. All right, let's take a look at the other ones starting from the left and moving over to the right. If we take a look at the 192 here, all right, how does that correlate in binary? Well, if we take a look at the binary number, and I'm kind of zooming up and down here, I know. We take a look at this first 192, then we have to decide what two numbers would equal 192 if we were to add them together. Well, the two numbers that add that up would be 128 plus 64. So therefore, we need to have those two bits turned on, because 128 plus 64 equals 192. You can see that reflected down here a little bit better. So we need 192. We have these two bits turned on. So 128 plus 64 equals 192. Let's look at our next octet, 168 here. Okay, trying to highlight it. There it goes. 168. To add those numbers up, what we would need to do is to add up a certain combination of numbers here as well. We know that we need at least 128 because 168 is bigger than 128. And then you can kind of eyeball this and try to come up with numbers. There's other methods that can be used that are more detailed in terms of doing this kind of IP addressing. But for our purposes, it's important just to know that we have to have some combination of numbers that add up to 168, and that happens to be the first octet at 128, this one at 32, and then this one at 8. Okay, so these three numbers add up to 168. Therefore, we're going to have a 1, 0, 1, 0, 1, 0, 0, 0. Okay, so just as a pop quiz, so to speak, what if I wanted this number right here to equal 169 instead? Where would I have another bit position turned on? Well, this right here, instead of being a 0, would be a 1. That way I'd add 128 plus 32 plus 8 plus 1. That would give me 169. All right? And then the 1's pretty easy. You can see that one right there. We already addressed that one. And then the 227, if we need that octet to be 227, we would just, again, add up a sequence of numbers until we are eventually able to get to that amount. So now, by turning on the bit positions in each one of these locations, we have 227. Now then, that's probably more information than you really need to know for the A+ exam. I don't think you're going to need to know all this binary and this numbering line and how to come up with those numbers. But the reason why I show them to you is because if you don't have an understanding for what this is, some other things related to IP addressing don't make as much sense. So let's move on and take a look at some of those other items. Now, as we take a look at the binary format of an address, you also need to understand how to identify when you look at an address, whether it's something called a Class A, Class B, or Class C address. You see, there are three primary classes that can be used. There's actually more, but these are the ones that you'll actually configure on a client computer. Now, the Class A address range is anything from 1 through 126 in the first octet. So, for example, a 5.6.7.8 IP address, that would be a Class A, because that's between 1 and 126 in the first octet. Remember, it was 5, and that was the first octet. So that would be a Class A. Then we would have a, on this also, there's a 0 in parentheses. What's that about? I put that there only to point out that if you look at the IP address in binary, the first octet will always start with a 0. And that is a visual indicator to you that that is going to be a Class A address. Also, you'll have Class B addresses, which the first octet will be anything from 128 up through 191. Any address you see that starts with one of those numbers, you can be guaranteed that that's a Class B address. And in binary, you can always identify that if it starts with a 1 and then a 0 in the first octet, then you know it's Class B. Same here. Class C always starts with 192 up through 223. The first three bit positions in the first octet, in this case, would be 110. So those are your visual identifiers to immediately look at an address, either in decimal format or in binary format, and to immediately know whether it's a Class A, B, or C. Now, for A+ exam objective purposes, you'll also need to know what subnet mask to assign to each one of those. Once you've determined that, you're looking at an IP address that is a Class A address. Then you'll have to put in the subnet mask of 255.0.0.0. Now, what is a subnet mask? This is used to identify whether or not a client is trying to communicate with a destination host that's on either its same network or on a different network. you can kind of think of it as, a filter. It's, again, going to be all binary. We're seeing it here in decimal format. But if you look at it in binary, that would be the first 8 bits, first 8-bit positions in the first octet would be all ones, because that would be 255 if you were to add up all those numbers from the number line. Then all the rest of these, of course, are zeros. Okay. Well, those ones kind of act as a filter to help identify whether or not a destination host that we're trying to communicate with is either on our same network or on a different network. For configuration purposes, just know that when you configure the IP address for a client and you're entering in a Class A address, then this is the default subnet mask you'll be able to enter in for that client as well. Now, in reality, this is what the A+ calls on you to know about. But in reality, rarely if ever will you set up a strictly Class A address. There's another level of IP addressing that you can go through called custom subnet masking. So that you might be using a Class A address, but the subnet mask you might use would be something like 255.255.240.0, which would essentially be a custom address. This allows you to divide up your network into more networks, but smaller hosts per network. And you would have to customize that. That's a whole different study, pretty much beyond our scope. But by default, you can see the default subnet mask. Again, you need to know that. Then these last 2 columns here, the number of networks and the number of hosts, that's just supplemental information. You don't have to memorize that for A+. But out of the box, so to speak, if you had a default Class A address, 5.0.0.0 as your network ID, for example, and it had this default subnet mask, that would mean that you would be able to divide that up into 126 different networks, and each network would be able to have over 16 million hosts. So you can see why we divide this up, because we wanted to make this more practical number. In smaller networks, very commonly you'll see this Class C address range, 192 dot something, and then usually you can put 254 hosts on those networks. Also, as you were looking at this, you might have seen something that looked kind of missing. Say, okay, we got 1 through 126 in the first octet, okay, but then we jumped to 128. What happened to 127? Well, that's down here. 127 is also a Class A address. This is important to know for A+ exam objective purposes. This is the loopback address network ID, 127.0.0.0. Okay. Now, if you take a look at a command prompt and you want to ping anything in that address range, okay, in that network ID, then all the addresses in that network ID are called loopback addresses. The purpose of a loopback address is that if you can successfully ping it and get a response, then you know that the TCP/IP stack is correctly loaded in the Windows operating system, and at least in terms of the software of it, that your IP health should be healthy. There may still be something wrong with the network card. There may still be something wrong with a hub or a switch in between, or a router or something else, but at least in your own house, so to speak, everything is fine. So by example, if I were to ping 127.0.0.1, that would be, and A+, as well as a lot of other people, consider this to be the loopback address, as if it's the only one. In reality, look how many addresses you have in a Class A address. 16 million. So the reality is, we have up to 16 million different loopback addresses. In other words, more than 16 million ways to ping yourself. Let me show you that another way. If I were to do ping 127.255.255.254, that's the last address you can use in the whole Class A address range. Notice that that also pings myself. Now also you need to know about this for the A+, and that is private IP addresses. Now what are these about? Well, you see, it used to be that when you wanted to get an IP address for your host inside of your company or inside of your university, that you had to go to an organization, the IANA, the Internet Assigned Numbering Authority, that would then dole out to you a range of numbers, a range of IP addresses that you could use. The problem was they gave away a lot of big address ranges early on to government organizations, to universities, and a lot of other bigger corporations. And it turned out that they ran out of addresses. So now we don't really have these addresses anymore. If you want to get one, you can't get them from the IANA directly anymore. You have to lease or buy them from an ISP or use some other kind of method. I don't know. Maybe they're being sold on the black market or eBay or something like that. So now that we cannot any longer get these addresses, we can use these private addresses inside of our own networks without having to be concerned about getting permission to use these numbering ranges. Okay, so these are available for you to use however you want to. Smaller subnets and smaller networks will generally use something in the 192 range. I actually use addresses in the Class A range. I'm on the 10.10. Here, I'll just show you. I'm on the 10.10.10.0 address. So IP config. If I scroll up here, you can see that my IP address on my internal network is 10.10.10.21. Notice that I'm using a Class C address mask for that. Now, I don't want to make things more complicated than they have to be, but internally like this, I'm certainly at liberty to use whatever subnet mask I want to. You still have to know that, though, that for the default subnet masks that you'll be using these up here for these address ranges. But anyway, that's my IP address. And I don't have to be concerned about other people having that. One of the key things about that is that this is a non-routable IP address as well. In other words, if I were to put this number, this IP address, on the public internet and connect my computer directly to the internet, I would not be able to access anything on the internet, and nobody would be able to touch me on the internet either, because it's not routable. Now, in a moment here, we're about to configure the TCP/IP version 4 properties for a Windows machine. We've been there before when we talked about other topics a little bit, but we'll be more specific here. And I also wanted to show you this diagram in advance first as well. So let's say, for example, that we have a IP address here on this computer, and we want that IP address to be 10.10.10.20. All right? Now, we also want to identify that we're in the 10.network, which, remember, that would be a Class A network. So normally you'd have a subnet mask of 255.0.0.0. I'm using a Class C subnet mask in this Class A network. So I'm just going to use 255.255.255.0. You'll see that here in the interface in a moment. But I want to show you this diagram so that you can have a better understanding for what we see in the actual TCP/IP properties when we make those configuration settings. Now, there may be other servers on the network here as well. For example, this could be a DHCP server. The DHCP server makes life real easy because you don't have to configure any of these clients. By default and out of the box, all of these Windows clients will automatically pick up whatever you've configured the DHCP server to issue to those clients, including their IP addresses, which DNS servers they use, what their default gateway is. All of those things will be configured through DHCP. Now, the only time you'd need to statically configure that, like I'm going to show you here in a moment, would be as if you wanted to make sure that a specific computer always had the same exact IP address. Because DHCP servers have leases, and that may only be a few days, and then that lease expires and it might renew a different IP address than it had before. But if I have a computer that I always want to know is an exact specific IP address, then I can set a static IP address for it. Now, in reality, you can also use something called a reservation in DHCP, but that's beyond our scope. But just know that using DHCP, that is still a possibility. It's just that if we want to set up a static IP address, we'd have to do so through the interface of the specific computer we're trying to configure that for. And then we would have a router here. That's what this is right here. That's my router. And the router, in this case, has two interfaces. One interface is on the 10. Network, so it's the 10.10.10. And then very often a router will end in .1 or .254. So often it's at the beginning or at the end of an IP address range. So I need to know about this interface IP address in order to properly configure my TCP/IP settings for my client. And then on this network, we have a totally different network range, a totally different network ID. 192.168.100.0, and here I'm just going to stick with the default Class C address that belongs to this this network anyway, and that will be 255.255.255.0. All right, and then here we also have a DNS server. Now, the DNS server does not have to be in the same family of addresses, so to speak, as the clients that it serves. So this computer down here, I can use this DNS server. I don't have to find a DNS server that's 10.10.10. 5 or something like that. I can use this one right here. And what happens here is when I try to find an IP, rather to resolve a name through DNS, then I'm going to look for this IP address, and I'll configure that in my static settings. The only way that this client is going to get to this server, though, is, guess what? Through this router. The router knows about both networks. So the router will say, hey, you're trying to find somebody in this network? Oh, I know who that is. That's this one right here. It'll resolve the name for me, and I'll be able to, actually it won't resolve the name, but it'll forward the packet for me onto this DNS server, and then it will resolve the name for me on the DNS server. Now, you may also need to know about something called a proxy server or a firewall server. This is a proxy server. Is not really a Microsoft name. There's several different products that do proxy for you. It might be something from Checkpoint. It might be something from Cisco, or it might be Microsoft's own ISA server. But there's several different servers that perform these proxy services for us. And what they do is they will take a request for a web page. So, for example, let's say out here on the internet, you're trying to find www.cbtnuggets.com, and maybe you want to watch, well, maybe it's this video. And you're watching it on this computer over here, okay? Well, your browser will be configured for a proxy server, and it will send all of its traffic through that proxy server. There's two reasons for that. Number one, it also acts as a firewall, and you may have more than one firewall involved in this. There can be an elaborate scheme of firewalls involved. But in a simplified diagram that we have here, it could act as a firewall as well. That would prevent internet strangers from weaseling their way into your network through this proxy. Okay, this is going to block that kind of traffic that's been unsolicited or uninvited. Okay, so we're trying to access an internet video like this one right here that you're listening to right now. And the proxy server, when it delivers that content back through here, it caches much of that content. And then what happens here is, let's say that this person here also wants to listen to an A+ video, and it's the same one even. Well, there could be a lot of that content that is still in the cache. So the next time when this client wants to access that, then it will just retrieve that out of the cache right here instead of having to go out to the internet again and use our internet bandwidth. So it helps to conserve on our internet bandwidth. That's the purpose, one of the purposes of a proxy server, and the other purpose, of course, is for security. And in reality, something like video content is not normally going to be cached, to be honest. Normally, it's going to cache stuff like static content on the page, like any text that it has, or maybe any GIF files, graphic files, those sorts of things. But something that's, a talkie, like a motion picture or something like that, is normally not going to be cached. However, the frame around the video player, any logos that we have, all that kind of stuff will be cached and delivered more quickly to the other clients that also request the same content. Now, also we talked about DNS here briefly a little while ago here. Let's get a little bit more detail about what DNS does for us. Let's say here, for example, that I've got a computer called PC2, and it's at 192.168.100.2, okay, something like that. Well, if this computer down here, if I'm sitting down here and I want to communicate with this computer up here, maybe first of all I just want to know if it's even there. So I might want to ping it. And we've talked about ping in the past, but what I would do is I would type ping followed by the IP address or the name of that computer. Now the reality is it doesn't actually ping a name. What it really does is it pings an IP address, but I don't know the IP address. So what happens is DNS will resolve that name for me. So when I try to ping pc2.nuggetlab.com, if that's the name of our domain, the DNS server will say pc2.nuggetlab.com is at 192.168.100.2, and then it will send a reply back saying that it's getting, receiving those ping packets. So the DNS servers resolve names against IP addresses. The same thing happens when you browse a web page on the internet. When you went to www.cbtnuggets.com, you probably didn't memorize the IP address for that web server. Instead, you just typed that into your browser. Well, an internet DNS server somewhere resolved that for you, and then you actually connected to it by IP address beneath, behind the scenes, so to speak. Now, by the way, we didn't always used to have DNS servers way back in the ancient times of the internet beginnings. It used to be just a single text file, hosts file. And this could be loaded into computers. And what would happen then is there would be a a correlation there. The host would have the name of the computer, and then next to it would be the IP address of the computer. And what would happen is this big file would just get passed around between major universities and organizations and so forth, and everyone was responsible to update it on their own. Well, you can imagine that got just out of control very quickly. That's what DNS resolves all of this for us, and it's much, much better. And I also want to talk to you about a kind of a troubleshooting issue with this as well. For example, let's say that again here I'm trying to connect with PC2. Now, if I'm able to connect to it by IP address, but I'm not able to connect to it by name, that tells me that the DNS server is down, because that would normally resolve this name for me. So if I'm trying to map a drive to PC2 and it just doesn't take, but it will map if I connect to it by IP address, then it's not getting its name resolved. DNS must be down. And I would simply be aware of that item. And just as a quick example, we'll look at ping again in a future nugget. But if I wanted to ping one of my own servers on my actual network here, I would just ping dc1.accusource.local, and it would send back replies to me. And unless the firewall is blocking those echo requests, which is what they're called in ping packets, then I can get a reply back, and it'll show me that that server is actually alive and well. At least in the sense that it can reply to me. Now, with all of this having been shown, now let's go ahead and go into TCP/IP properties. What kinds of things would I configure if this computer was 10.10.10.20? Well, I would use the following IP address. Correlating to this right here, I would enter in the IP address of 10.10.10.20, and then the subnet mask. If I was going to stay with a Class A subnet mask, I would, of course, leave it just at 255. Notice that the TCP/IP settings here pre-configure the default subnet mask for us at 255, and I only need to change that if that is actually my intent. So I'm using a Class C address for my Class A address right up here, but I'm using a Class C subnet mask. And then for our default gateway, that would be at 10.10.10.1. Well, so that's what I need to type in here. Default gateway is your router's interface, 10.10.10.1. All right. And then if I want to do a static IP address for my DNS server, that's 192.168.168.100.5. And that would pretty much be it. I really wouldn't have to do much more beyond this right now, except for click OK. One thing I recommend that if you're working with Windows 7, and of course that's not on the exam, but if you're working with Windows 7, this is very handy. You can validate settings upon exit. So it'll check to make sure that there actually is a server, DNS server, with that IP address. That this default gateway actually exists. That this IP address has not already been taken by another computer. So, in fact, I know at least one of these things is wrong, so I'm just going to kind of go ahead and click OK here. And you can see here that in Windows 7 and Windows Vista is similar to this when it comes to network problems. It's detecting problems, and it's going to go through a series of troubleshooting steps, and we're not going to continue on that right now because I deliberately misconfigured those settings. But that's how I would configure it if I wanted to set in static settings for you. And you need to know how to do that for the A+ exam. And then as far as the proxy settings are concerned, you configure that a number of different ways. This can be set up automatically so that you have a script that runs and that will configure automatically all of your clients, and that's a very simple way to work it. Or you could configure it manually, and I'm going to show you the manual way just so you can see that I've kind of done the hard way, so to speak. And what you would do with that is you would open up Internet Explorer, you'd go to Tools, Internet Options, and then you would go here to Connections, and what you're looking for is LAN settings. That might just as easily say proxy settings. Okay, so you just click that. And then here you can automatically detect the settings, and then this is where with certain types of proxy servers, it will respond to this automatic detection and fill in all the settings that are necessary for you to be able to access that proxy server. Or you could use an automatic configuration script, and you'd have to just type in the address of whichever server had that script for you. Other thing you could do if you want to do the whole thing manually is you could use a proxy server for your LAN right here, and you just enter in the IP address of your proxy server. Let's say it's, I don't know, 192.168.100.20, you know, and then that would be it. By default, proxy servers appear on or use port 80, but you can change that if you want to, but pretty much you're good to just leave it at the defaults for most purposes. And then you can bypass the proxy server for local addresses. Remember I told you earlier that these private IP addresses that we've been looking at are not routable on the internet, okay, like 10.10.10. and 192.168.100. These are not routable on the internet anyway. So if I'm going to go ahead and communicate with maybe another server here somewhere, maybe it's an intranet web server on this network segment up here, well, I'm not going to go all the way out to the proxy and then all the way back into my network, because that would be kind of redundant, and it's not really a security concern. So that's just one of the things you can do, is to only use local, to not use it for local addresses. Oh, another thing that the proxy server does for you is that it performs NAT translation, network address translation. Remember I told you these IP addresses are not routable on the internet? Well, how am I going to go out to the web server out here that I'm looking for and have it tell it to return to 10.10.10.20 a specific web page? It won't be able to do that because the internet routers will not be able to route to that destination. So what happens is, when I try to make my request and I go through my proxy server that I'm configured for, then the proxy server will send the request out for me on a public IP address. Let's say it's 27.5.1.2. Okay, that's a public IP address. So it'll use this public IP address to communicate with the internet at large, and the web content will come back to the same IP address. Then the proxy server keeps a table of who it was that originally requested that web content, and then it will send it to whoever it was that originally asked for it down here at 10.10.10.20. So that's what we call network address translation, where we take an internal private address and then we translate it, so to speak, into a public address that can be used on the internet, and then retrieve it back through the proxy and then back on down to its destination. Network address translation. Now, we also want to talk about DHCP. A full description of DHCP and configuration of it is beyond the scope for our course, but here I've got a Windows Server 2008 R2 DHCP server, and we're looking at the console for the DHCP service there. Notice that I will have created an address pool here, or a scope, if you want to look at it that way as well. If I right-click on this and choose Properties, notice that it starts at 20 and it ends at 254. All right. Now, when we configured it that way, why didn't I start at 1 through 254 instead? Because if you look at the address pool, it's 20 through 254. Well, the reason why I didn't assign 1 through 19 is because those are statically assigned addresses that are given to other network devices, printers, servers, and other things like that within my network. So I never want a client to get a duplicate address for something that's already been statically assigned. And that's one of the things you can do there, is to just narrow the scope of addresses so you exclude those that you want to be always static in your environment. And then returning to our diagram here, let's take a look at what would happen if the DHCP server went down. If that happens, then you have a client that's trying to get an IP address, then it may self-assign itself an address of 169.254.something.something. This is what we call an APIPA address, which stands for Automatic Private IP Addressing. Anytime you see a computer with this address, this means that it was not able to receive an IP address from the DHCP server, and so very likely that DHCP server is down. In this nugget, we took a look at networking. This was part 3, where we started off by talking about various protocols and ports, such as TCP/IP, HTTP, HTTPS, POP, IMAP, SNMP, all those sorts of things. And also we talked about the ports that they need in order to be open. We'll talk about firewalls at a later point in time, but you might need to open up certain ports in the firewall so that you can provide a certain service for one of these protocols. We took a look at IP addressing. Remember, it's really binary. That's how your computer sees it. Then you can break it up into octets to make it a little bit easier for humans to see. And then to make it even easier, we can look at them in decimal. But you have to understand the conversion from binary to decimal in order to understand how that is actually done. Although for the A+ exam, you don't need to understand that correlation exactly. I just think that it's a better rounded knowledge if you have some understanding of it. But we also took a look at address classes. Definitely need that for the A+ exam. And there's documents you can download from nuggetlab.com which identify the various classes, their subnet masks, and other things such as the loopback address range. We took a look at TCP/IP configuration. How would you actually set up, for example, a static IP address? If everything's done automatically, it's actually going to be using DHCP. But we took a look at the static configuration as well as some of the servers and roles involved in a network. We looked at DNS as one of those servers, which resolves names to IP addresses. DHCP, which issues addresses for you so you don't have to do a static IP configuration. Proxy servers, which are good for security as well as accelerating your internet performance. And then also automatic private IP addressing, which is the kind of addresses you might get if your DHCP server is down. Well, I hope this has been informative for you, and I'd like to thank you for viewing.